Okay, welcome to the Wednesday, May 31st joint food ontology work group discussion. And this morning we've got Katherine Thornton presenting demonstration of sourcing multilingual labels for food items with FoodOn IDs from WikiFCD data as well as from Wikidata. And Chris Mungall as well, presenting OntoGPT, a large language model driven tool to map content to LinkML schemas, with one happening to be a recipe model. So looking forward to both of these things. And are there any announcements people want to make before we get into presentation mode? If not, I hand it over to you, Kate. I mean, Kat, sorry.
Thanks, Damien. Okay, I'll go ahead and share my screen here.
Okay, good.
Are people able to see a slide called multilingual labels in WikiFCD?
Yes.
Okay, great. Before I get started, if anybody would like to follow along with a copy of these slides, there's a link here to the deck itself if you'd like to follow along that way. And I want to introduce my collaborators, both of whom are here today. Dr. Mika Matsuzaki, our nutritional epidemiologist, Kenneth Seals-Nutt, who is our computer scientist and responsible for the software engineering that drives a lot of the parts of our project. And I'm Kat Thornton, and I'm an information scientist, and I mostly work on the data related to this project. So a quick introduction to WikiFCD. WikiFCD is a public knowledge base of food composition data drawn from a variety of international sources, all published food composition tables. And the data in WikiFCD is referenced back to the original sources where we found the food composition values themselves. And WikiFCD contains many multilingual labels for food items. And these multilingual labels are drawn from the original source publications where we found the food composition values. We also have numerous mappings to FoodOn from our food items. And we also have mappings throughout WikiFCD to Wikidata for several different classes of items. And the last link on this slide is the link to WikiFCD itself. It is public on the web, and you're welcome to visit and browse the data or reuse any of the data in WikiFCD in your own projects. The question that we'll be discussing today is it possible to source multilingual labels for food items with FoodOn identifiers from public knowledge graphs like WikiFCD and Wikidata? And to get into the why of this project, why are we interested in having multilingual labels in WikiFCD? Well, WikiFCD is a global knowledge base, and we hope that people who are interested in food composition data from many different language backgrounds will be able to use our knowledge base. And by finding additional multilingual labels for food items from other public knowledge graphs like Wikidata, we can enhance the breadth of access points that we can provide so that people searching in languages in addition to English will be able to find food items and their relevant food composition values more easily. Our goal here is really to reduce data disparities and to provide convenient web access to food composition data for a wider audience. And we asked ourselves, if we're doing this work for WikiFCD and for our own project, is there a way that we could also present or share this data with the FoodOn community that might be relevant for members of the FoodOn community? So many of you are probably familiar with this logo for the Wikipedias, and many of you may read Wikipedia in one or more language versions. But today we want to remind everyone that Wikipedia is available in currently 320 different languages. So this is really a large range of human languages that are represented. Of course, there are many more human languages where we don't yet have Wikipedia coverage, but this is already a great start. And for anyone who is familiar with the Wikidata project, all of the languages that are available, that in which different language versions of the Wikipedias are available, are also supported by Wikidata. And something interesting about these projects is that while Wikidata contains all of the inter-wiki links between the different language versions of the Wikipedias, Wikidata also contains additional labels that are beyond what is found in the Wikipedias. So there isn't a one-to-one match between a language version of Wikipedia and a language label for any given item in Wikidata. So this enriches the breadth of possibility for finding multilingual labels from Wikidata as well as the Wikipedias, giving us a even broader pool of labels that we could potentially reuse for the food items that we're interested in. So we wanted to know if it's possible to source these multilingual labels from our public knowledge graphs. And in order to do this, we focused on a sample data set of 6 food items. So we looked at the foods apple, chocolate, rice, purslane, kale, and oregano. And then we wrote a set of Sparkle queries on the Wikidata Sparkle endpoint and the WikiFCD Sparkle endpoint to collect multilingual labels from the different language versions of the Wikipedias, from Wikidata, and from WikiFCD itself. So how did we choose this sample data set of food items? We were looking for a combination of some foods like apple, chocolate, and rice that would be, we guessed would be well represented across many different languages. And then we also chose items like purslane, kale, and oregano, where we weren't sure what the coverage would look like, but we suspected that it might be more difficult to find multilingual labels for these less commonly discussed food items. And then through writing these Sparkle queries, we identified different subsets of the Wikidata graph from which we could pull these labels. And altogether, we came up with 5 subgraphs that we looked at, and we sourced labels from each of these 5 subgraphs for the 6 food items in our sample data set. So our 5 subsets are the article titles from different language versions of Wikipedia. So for example, this is in English, the article about apple has the title apple, but in other language versions, the title for the article describing the same fruit, we reused those article titles as the multilingual labels from each of those different languages. We also looked at the Wikidata item labels. And so on the Wikidata item itself, labels are stored in all of the different languages that Wikidata supports. So we also looked at that subset. We looked at a specialized property in Wikidata called taxon common name. And so this is another place where labels related to food items are stored in Wikidata, and it is unrelated to the item labels on the Wikidata items themselves. So we wanted to investigate, would we find additional or different labels in the taxon common names? And then it looks like I'm missing a bullet point here. This should be its own line. The common names that we store in WikiFCD itself, and so these are coming from the food composition tables that we consult to get the food composition values for WikiFCD. And then the last subset we looked at is called the Wikidata lexemes. And so the Wikidata lexemes are their own namespace in Wikidata. And this is an entire namespace devoted to lexicographic data. And so lexemes in Wikidata essentially represent words or parts of words. And there are some lexemes for food items in the lexeme namespace. So we also consulted that to see if we could find additional or different labels from that subset. So you might be wondering, how is the coverage? Well, the coverage is different across the different subsets, and it also varies for the different food items that we looked at. So we were definitely successful in picking a subset of, or picking a sample data set that showed quite a bit of diversity in what's possible for collecting names. So to give you a sense of what some of this data looks like in Wikidata, this is a screenshot of the Wikidata item for kale. And this is just a partial screenshot showing some of the languages and the labels that we found. So here on the left, you can see the name of the language that provides the label, and then the label itself here. This middle column is for a description, if a description has already been added in the different languages. And then this last column is space for aliases, and these are defined individually for each language. There's space to store additional alias information. So when we're talking about the Wikidata labels subset, we're talking about all of these labels across the different languages supported by Wikidata that we were able to collect through our Sparkle queries. So this is another screenshot showing the coverage of the Wikipedia article titles for Apple. And I'm going to show this data in more detail in just a second. But if I just share it against this first example, where we're showing the labels that we have sourced from the Wikidata lexemes, if you see the grid colored in, that means that we did find a label. And if it is just the neutral color, that means that we did not find a label. So just quickly comparing these two, the subset for the Wikipedia article titles, we found many more potential labels for Apple than we did from the Wikidata lexemes. And so we'll talk about these details in more depth in a minute. So sorry that the numbers are not looking that great here. But you can see in this table that the counts of the labels that we found across the different subsets varied quite a bit. So for purslane here, we only found 2 labels currently in Wikidata, 40 Wikipedia article titles, and 2 lexeme senses from the lexeme namespace. But if you look down here at chocolate, chocolate had 118 Wikidata labels, 144 different language version article titles from Wikipedia, and 24 different lexeme senses. So I'll show you some examples of what the actual labels that we found were in just a minute. But the point of this table is to illustrate that there was quite a bit of diversity, and that the more popular food items like apple, rice, and chocolate, we found more labels in Wikidata and overall. And for the less popular food items, we did find fewer. And then that first table was showing the Wikidata labels, the Wikipedia article titles, and the lexeme senses. And then this table is showing the taxon common name subset that we looked at. And this subset was interesting because for many of our food items, there were actually multiple common names provided per language. So our counts here, this is the total number of taxon common names that we found for these. Here you see the, the scientific name for the taxon from which those food items were derived. But when you look over here at the number of distinct languages, you see the counts are quite a bit lower. And this is because there were a lot of food items for which some people provided multiple Portuguese common names, for example. And so this subset was particularly noisy in that we don't know as much detail as we might want to know about why are there multiple common names provided? Do they vary regionally, or are some of these actually not for the same food item, but a closely related food item? So this was assigned to us that for this particular subset, there could be relevant data here, but it's definitely a subset that we would need to treat a lot more carefully. Whereas the previous subsets that we described, they generally just had a single label per food item per language. So now I'm going to show this interactive web app that Kenneth Sealsnut created to give the FoodOn community a chance to explore the labels themselves for these 6 sample foods. So what you'll see here, this is an interactive web app that you can use to explore these labels yourself. I have the link in the slides, but you can also see it here. I'm mindful of the time, but I want to go through this a little bit. So each of these colored areas means that we do have a label for this language. So when I hover over the 2-letter abbreviation, or sometimes 3-letter abbreviation for the language, you'll see in the gray rectangle there the label itself that we found, and then in parentheses the source language from which that language came. So if I just slowly move across these here, you can see all of the different labels that we were able to find. And then the design of the layout here is designed so that you can quickly compare across the different subsets and get a glanceable sense of what is the coverage like per subset and how much overlap there is between these different subsets. If we look at the common names from WikiFCD, you'll see that currently we only have 1 common name for apple in a language beyond English. But if we look at the Wikipedia articles, you'll see that we found many different labels for apple that could potentially be of interest to the FoodOn community. And over here, you can select between our different food items from our sample data set. And then in this dropdown, you can select the different subsets from which we found labels that you may want to explore. Okay, going back to the presentation. I'll just quickly wrap up here. I know that we have another presentation. So the benefits of having multiple subsets across which to compare. We have a larger number of total labels. We can do cross checks between the subsets to give ourselves greater confidence that the label we found is a reliable label. And some of these subgraphs have detailed references. So of course, all of these food labels can be sourced either to Wikidata, Wikipedia, or WikiFCD itself. But then within some of the subsets, we may also have an additional reference to some kind of published source, whether it's a book, a scientific article, or some other type of dictionary or reference source, so that we would know exactly where that label is coming from. And that might help us get a sense of how trustworthy the label might be. And just to emphasize the power of knowledge graphs and peer production here, the enabling technologies of the knowledge graphs themselves, RDF as a data model, and Sparkle allowed us to combine data from multiple different sources quickly with just a few dozen Sparkle queries. And then the peer production model that is used in the communities around the different projects of the Wikimedia Foundation is really the key element that created the rich availability of multilingual labels in these projects. When we have multilingual contributors, they're actively creating multilingual data, and it is the power of all of these people coordinating through the infrastructure of these projects that has really built up such a valuable store of multilingual labels that could potentially be of value to many audiences beyond just the audiences interested in these projects themselves. Multilingual labels coming from knowledge graphs are definitely one of the strongest advantages of knowledge graphs. And I put a link here to a more in-depth discussion that mentions the value of sourcing multilingual labels from these public knowledge graphs. And then to close, the questions that we wanted to bring to this audience, we wanted to discuss the interest in increasing the numbers of multilingual labels for the food items in FoodOn, and see if that is of interest to this community. We wanted to discuss potential workflows for how these labels might be reviewed by FoodOn curators if they are of interest. We'd be interested to know at what interval would periodic refreshes of this data be valuable, and talk about potential workflows for refreshing this data every once in a while. And we'd love to know what are the target languages that the FoodOn community might be most interested in sourcing languages or sourcing labels for, as a first step in exploring the potential of sharing some of these labels with the FoodOn community if they are of interest. So with that, I'd like to say thank you, and I'll pause here for questions.
Katherine, that's so great. And Kenneth and Mika, thank you for contributing this and tackling this gigantic data crosstalk challenge. Okay, let's straight to questions. Warren.
So question, you're using Wikidata data in order to get this done. What has been the improvement over, say, DBpedia or multilingual labels?
Great question. So the advantage of sourcing it from Wikidata is that Wikidata is still, Wikidata is open to active editorial curation. And so additional labels are being added, not necessarily to food items, but to items across Wikidata all the time, every day. And so this corpus is still growing. Because the data in DBpedia is machine extracted, there is a delay in when data gets updated into DBpedia after it is curated by the communities of the Wikimedia projects. So I guess the data in Wikidata is still actively growing. And if we see any data that is incorrect, we can quickly correct it in Wikidata, as opposed to if we found something incorrect in DBpedia, in order to update or correct that, that would be a longer process.
I'm going to ask one thing that's tangential to Warren's info to me. Agravoc has a pretty interesting looking multilingual mapping, and yet Warren tells me some of it's machine generated and can't be trusted. Did you at all consider Agravoc as one other source for the multilingual translation?
Well, I also heard Robert Warren describe that limitation of Agravoc in a previous meeting of this work group. And so we did not explore Agravoc. We wanted to offer this approach as what would it look like to source it from these projects, and then others who may be more familiar with the Agravoc data could compare this with what they're finding from Agravoc.
Mm-hmm. Okay. We've got questions coming in on the meeting chat. So Naomi asks, do you assess the quality of your results for food components? I think that might be getting at one of your resources might be reporting a couple of hits on a term, but another one, but that might actually just be returning, say, the scientific name for apple being used in the label column.
Yeah, so we have not yet gotten to any kind of assessment of these different labels. This was a data collection exercise for this sample data set from these 5 subgraphs to see what types of, what did the coverage look like? And, you know, is this possible? So we were exploring that in this first study, but the quality of the labels is certainly something we're really interested in, and we've discussed future work where we could take a look at the quality of the labels, but that wasn't an aspect of this first study.
Yeah, okay.
Sorry, if I could clarify, by quality, I meant the quality of the food composition, not the quality of the labels.
Oh.
Because ultimately the use of data will be applied to you know, what's in a food that may or may not impact wellness or health. And so therefore the quality of the number becomes very important. And that's what, so I guess I misunderstood the level at which this was doing it. So
thank you for the clarification. So in WikiFCD, we represent the data from the original published sources in which we found it. We do not clean or adjust the data values in any way. We present them exactly as we found them in the original published source, and we do not assess the quality of those values. We are presenting them in a more convenient web-based format, and we are trying to be faithful to the original source, so we are representing the original data as we found it.
Okay.
Just to piggyback off of that, because it's relevant to that question and topic, is Kat, I lead Food Data Central, and I posted in chat that I have some questions on that, so maybe we can meet and discuss that further at another time.
Um, wow. Well, we're pinching into Chris Mungall's time, but let me just say, what I see you folks doing is step one of the process of identifying possible terms. Next step, harmonizing, choosing a sort of focal identifier upon which to create reliable mappings to the different languages from, say, a FoodOn ID or a WikiFCD food term ID. And that is inviting, you're saying, sort of the power of community curation. And we also see that over on the FoodOn side. I don't know if any of our FoodOn curators themselves would be able to, core curators would be able to help with the translational side of that, because we don't speak other languages really except Magali. So that's a challenge. But what I will say is that what FoodOn is interested in is externalizing our synonymy. Right now, we've got synonyms baked right into the ontology, and we're curating them like manually there, which is asking people to come in and manually curate into the ontology. I'm interested in this Obo Foundry technology called SSSOM, which is a simple TSV mapping table that allows you to take one term and identifier and map it off to any other language term and resource, ontology resource, or Agravoc or other kind of terminology. So we would move our synonyms into this and then make that the place that we automatically bring in our synonymy, multilingual synonymy. And that means that opens it up to be more of a resource that's managed and edited by several communities, not just the Ontology and Obo Foundry community. Okay, I think we're going to have to park. Maybe people can address some questions as is happening in the meeting chat, but we need to move over to Chris's presentation now, which should be actually kind of aligned, I bet, in the LLM possibilities.
I think so. Yeah. No, I'm actually quite interested in topics like using LLMs for translation as well, but that's not what these slides are about. These slides are about a framework we developed recently called OntoGPT, which allows kind of essentially melding ontologies and large language models. And I'm going to be talking about how we're, a little kind of fun application we developed using this for scraping recipes from the web. So even though the overall framework is designed to be used for multiple different domains, and we primarily, we're mostly NIH funded and DOE funded, so we tend to work more in kind of like general biological and environmental domains. This is a nice little kind of like a fun application of it. So the basic idea here is that we'd like to be able to extract semantic recipes. And what I mean here is to go from maybe recipe descriptions that you can find on the web that are in either maybe free text or they're kind of like semi-structured. And you want to extract it into some kind of semantic form such that you're able to, ask kind of like different queries of this. So like find me all recipes that don't involve the use of wheat, and maybe kind of like filter them by the calorific content or something like that as well. But it's hard to do that if it's all in free text. And one challenge with extracting kind of like semantic representations of things like recipes is a recipe is actually quite a complex object if you want to kind of like pin it down to, the actual underlying kind of like food entities in them, the quantities used, the measurements used, and even if you want to kind of go down to the level of the planned process for making the final food item from those individual recipes, all of the different kind of like steps involved. So so we like to represent things like this using semantic schemas. We have a framework called LinkML that can be used. It's essentially kind of like, you can think of it like JSON schema on semantic steroids, or similar to kind of like Shackle and technologies like that, if you're familiar with them. But at the end of the day, it just allows you to kind of like model things like recipes in a nested fashion. So here you can say a recipe consists of some metadata, one or more ingredients, one or more steps. The steps themselves, consist of some kind of like action, some kind of utensil, and then maybe a number of inputs and outputs. And those inputs and outputs themselves are complex objects that can be broken down into FoodOn classes, unit ontology classes, and quantities measured using kind of like literals like XSD float and so on. But ultimately, our target here is not a database, but it's actually a kind of rich ontological representation of these recipes. So this is to me the kind of like the dream of any kind of like semantic extraction is to go into something like this. So this is showing a screenshot of Protégé and how we might want to kind of like classify these different recipes and make use of kind of like OWL technology to be able to do automatic classification, the way I'm sure you're all familiar with how it works in ontologies like FoodOn, so that you can kind of automatically classify things under meat recipes or recipes containing milk and so on based on their underlying kind of like ingredients. And you can see on the right of the panel here, that we have in OWL a kind of like a nice kind of like nested representation, kind of analogous to our schema here. And so there's a lot of advantages in going to this kind of OWL T-box representation. You get the automatic classification. You get automated kind of validation in QC. You can ask kind of like complex queries that make use of reasoning, and you can just do plain kind of Sparkle queries as well. So it's a lot of work to kind of like manually extract recipes. In sitting in front of a tool like Protégé and just entering this by hand, it would take a very long time. So we asked, is this something that maybe large language models can help with? So if you are just maybe a quick kind of show of Zoom hands, how many people have played with kind of like ChatGPT so far and are kind of somewhat familiar with it? A few there, yes, yeah. So if you're not that, I think most people have kind of like read a lot of the various news reports and so on at the moment, but just to give you the kind of like the briefest of introductions here, one of the things that make some of these large language models so different from machine learning technologies in the past is their generality, and the ability to essentially kind of like follow instructions that you kind of provide this. And this essentially allows them to kind of subsume a lot of the existing kind of approaches that we used in natural language processing before. So back in the old days, we would old days being pre-2023, we would maybe train dedicated models for specific kinds of tasks, like say sentiment analysis, but kind of post GPT-3 and so on, we're realizing that there's actually a lot you can do with these very general purpose models by just kind of providing kind of in context information, or even using kind of like zero-shot learning. So rather than kind of like training a data set specifically on sentiment analysis, you can just kind of give it some examples and say, here's some examples of positive, negative sentiment. Now classify this statement. And we kind of see this pattern again and again with large language models. So we set about developing a toolkit called OntoGPT. You can find it on GitHub. Come along and give it some stars. And it's a Python library that interfaces with the OpenAI API, and also a kind of command line toolkit. It's got various different kind of components within it. And I'm going to be talking about one particular component called SPIRES, Structured Prompt Interrogations and Recursive Extraction of Semantics. So this is basically extracting kind of representations of implementation of semantic schemas from pretext. So the basic kind of workflow is shown here. You provide it with two inputs. So you provide it with the text that you would like to extract information from, but you also have to provide a schema as well that tells the model exactly what it is that you want to extract. And right now that schema should be represented in LinkML. We've got kind of like tools that will go from Shackle and JSON schema and relational databases to LinkML, but there's a lot of advantages to just natively authoring directly in LinkML, and I'll come to a few of those. And then the basic approach is that it does a recursive descent of the schema tree issuing queries to, at the moment, it's hard coded to use the OpenAI GPT API. And then as it kind of like, it builds out the kind of like the tree structure from this parse, it'll kind of ground the terminal elements using external vocabularies and ontologies such as FoodOn. And then as an optional final step, you can kind of like convert this into OWL. So the basic idea here applied to the recipe domain is that you would author a recipe schema like the one I showed earlier. You know, again, this can be kind of like quite kind of like detailed and nested, you know, kind of breaking down a recipe into parts and subparts. And then you can just kind of like feed it text that you can, you know, either complete free text or semi-structured text that just comes from like, you know, places like recipe websites and so on, and then get out a structured representation and eventually some OWL as well. So I'll kind of walk through with an example of how this works. And the basic idea is actually, you know, pretty simple. The overall idea is that it follows something that we call kind of like schema-driven prompting. And essentially we take the LinkML schema and we compile it into prompts that are fed to the OpenAI GPT API. So what it will do is it will start at the top of the schema, the overall recipe object, and it'll construct a prompt based on the immediate attributes of that schema element. So, you know, a recipe may have elements, label, description, categories, ingredients, steps, and so on. And it will just essentially kind of automatically construct a prompt that looks like what's in the brown box here. And then it will feed the text into that prompt as well. And then it will send that off to the model to get back the immediate results. And so what the model will give you back is something that is not a fully structured object, but something that is kind of like partially structured. You can see it gives us, you know, just basic simple named entity extraction of things like the label and the description, but it will also kind of like give us a semicolon separated list of all of these different attributes. Now it's still giving us this list as essentially semicolon separated strings, but then we can do, what the tool will do is we'll do a further pass through, take each one of these individual string elements, such as this one here, this first step in making our recipe here on medium heat, melt the butter and saute the onion and bell peppers. And it will do another pass through, recursing down the schema. This time it's going on to the step element and say, okay, step has the following attributes: utensils, inputs, outputs, steps, and so on. Automatically construct that prompt and then feed in this this kind of like this element that it got from the previous iteration, and feed that into the model as well. So this time it will pass in this and it will extract out the actions, the inputs, and the outputs. And in this particular case, it doesn't, you know, the text didn't explicitly specify any output, but it specified some inputs there. And again, we're still not fully at the end goal here of having a kind of like a semantic representation of the recipe. We still have kind of like free text labels, but it's essentially done the named entity recognition part for us. And then we can essentially just go ahead and ground this using ontologies like FoodOn. And so kind of like, grounding each one of these in turn. And the way that this works is it makes use of something in LinkML called dynamic value sets. So in LinkML, you can say, you can any element in your schema, you can say the values of this part of the schema must be taken from, you know, for example, this branch of this ontology, and there's actually a kind of like a full kind of like Boolean kind of graph expression language, so you can kind of construct your own kind of like essentially kind of queries that say how different parts of the schema can be filled in. But in this particular case, we might just want to say that the inputs and the outputs must be taken from food product in FoodOn or any subclass thereof. And so basically this essentially helps guide the grounding task so that it's not trying to match on irrelevant ontologies for that particular data type or on irrelevant branches of the ontology. And it can make use of our Python oak tool for doing this, or you can also plug in your own, plug in kind of like if you've got an Onto portal endpoint covering, what you like. So, there's, if you're not familiar, kind of like Onto portal is like the generalization of BioPortal, and there's kind of like AgroPortal, EcoPortal. I'm sure many of you are familiar with, or even kind of work on some of these as well. So you can kind of like plug in any vocabulary from anything that's in Onto portal, or anything that's in Obo, or anything that's accessible via Oak. So what does it look like at the end of all of this? Well, the primary output is essentially a nested YAML description. And you can see it's got kind of like all of the kind of like literals, like the labels, the descriptions, and so on, categories. And then as you kind of like recurse down, you can see it does maybe a somewhat okay job of kind of like grounding things eventually in vocabularies like FoodOn and the unit ontology. But what it, where it fails to ground this, it will essentially kind of like create ontology terms on the fly. And that's where you see these things that say auto salt or auto pan. So at the moment, we've not tried plugging in any vocabulary for things like utensils or actions. I'm actually interested. I'm not really an expert in this domain. I'm interested in all your thoughts and what some good ontologies to use here are. And to me, this is useful because it points us at things where we might want to kind of like plug things into the unit ontology, or plug things into in FoodOn. So it interestingly, it didn't manage to ground on salt. I bet if we plugged in Kebi as a vocabulary, it would find the Kebi term salt, but that's not actually what we're we're interested in. So I think it would be nice if maybe FoodOn included just a bit more kind of like common terminology for kind of like certain things like just salt, which obviously in this context means something like table salt and so on. So I think it's a good tool for being able to identify potential kind of like terminological gaps in or conceptual gaps in existing ontologies. But then we can do another step where we take this YAML and then we feed it through a tool called LinkML OWL. And this will essentially map this to a class-based or T-box representation. This relies on certain kinds of annotations being present in your schema that tells you how you interpret the different schema elements as OWL constructs, like objects and values from, equivalent classes, that kind of thing. But this is actually very powerful because it gives you a kind of full semantic representation that is amenable to our reasoning and automated classification. So what you're seeing here on the right, this is all of the leaf nodes here in this ontology were derived entirely automatically by scraping from the web. These intermediate kind of like grouping classes, they were manually authored, but they are kind of like, they have trivial logical definitions. So meat recipe is just defined as being any recipe that has parts of meat or meat product, FoodOn meat product. And then that will allow us to essentially automatically kind of classify this representation. So you get the full nested queryable representation over here. You can see we're kind of like cheating somewhat, like it's got the values are being represented as strings, and that's just because there's a few things we've got to resolve. Like sometimes values are actually single simple literals, and sometimes they're like ranges, between 1 and 2 and so on, and things like that. So so we haven't really, the recipe use case was a bit of a side project for us. We've not really fully evaluated it on recipes. I don't know exactly what kind of gold standards you would recommend for evaluating on the recipe task, but we did evaluate it on chemical disease, relation extraction. This isn't really taking full advantage of the approach, because this is really just extracting kind of simple triples rather than a kind of like a full ontological representation. And we find it does, it doesn't beat the best tools in this area, but the best tools are actually kind of like specifically trained on these individual domains. And the advantage of the advantage of our approach is the kind of like the generality. It doesn't need any kind of training data in advance. So we're actually kind of extending this. We've got a number of different kind of schemas or templates within OntoGPT at the moment. So You can extract recipes, you can extract drug mechanisms. I'm actually very interested in extracting biological signaling pathways, which in some ways are very similar to recipes. They're just kind of cellular recipes for how you make things or control things in the cell. We've got various kind of like templates for doing things in the rare disease area and so on. We've got a kind of like just a little kind of like command line tool as part of OntoGPT that makes use of I forget which Python module that will kind of like do some of the kind of like the scraping of the text from the recipe from online sources. So you can give URLs from All Recipes or Epicurious. I think there's about 20 different kind of like websites that will work with this tool that you can use. And if you want to contribute your favorite recipes, then did I put a URL? Yes, sorry. I'll send the slide link later on and this URL later, but anyone can go and make a pull request here, and then we'll include your recipe in this little demo recipe knowledge base that we're building. So yeah, just with that, just a few future developments. We're extending the schemas to cover more of the life sciences and the environmental sciences. Yeah, knowledge extraction is not the only ontological application of LLMs. We've got a few other applications we're working on. One we're quite excited about is something Damien mentioned, SSSOM, the mapping framework earlier on. So we're actually developing something that will enhance SSSOM mappings using large language models. We're interested in things like kind of automating workflows as well. And we're very interested in being not dependent on the OpenAI API, because we want people to be able to kind of like plug in things that are not closed source there. And so we welcome all contributors. And just with that, just to kind of like thank everyone involved, and particularly Harry Caulfield, who's the first author on the Spires paper and who built a lot of this framework. And if there's time, I can take some questions.
Yeah, you're supercharging the AI into our sector here. So it's amazing. Of course, refining the model, the recipe model, is high in my priority list too. And just to mention, in Sherbrooke, in a month and a bit, well, it'll be June, July, 2 months, we'll be presenting the FoodOn recipe model and trying to find the crossover to what you're doing there. Okay, questions?
I'll see there's a few in the chat. I could just. Do you want me to just go through the ones in the chat, Damien, or?
Yeah, I mean, there's a lot of comments, starting with state value property as a way to contend with, I guess, entities that have had stuff done to them, and we're not quite sure what was done, but we have a name for the state they're in now.
Yeah, I don't know if you've got any recommendations there. In some ways, it's almost like it would overlap a bit with the action vocabulary. We want to be able to say these things have been chopped, these things have been boiled, and so on.
Right. So that's a priority coming up. Tarini and I will be presenting on upper level process ontology that yields from chopping and boiling these states that we need names for. So it's a triumvirate of process, quality, and material entity that are a result of that. Those language pieces need to be in our language need to be tied together. Okay, so yes, and then just Obo Foundry, we need a vocabulary for laboratory processes as well, because boiling, whether it's in the lab or the kitchen stove, needs to be the same term.
Yeah. I looked at DBpedia there, but I don't know, I didn't see anything immediately obvious as a kind of like a candidate starting point for that.
Yeah, Magali.
Sorry for my bad English. Thank you for the presentation. It was really amazing. I am not an expert, nor in ontology or in NLP, but I am very interested in your approach. I am not sure to have understand what is the chicken and what is the egg. I mean, you need ontology to classify, but you first parse the segments, the phrase segments. So I didn't really understood how do you know what is the step in the recipe? Because you say then you can separate them with semicolon, which is fine to have some formatted structured data. But how do you make this? This is some kind of magic for me.
Yeah. Well, just to address the kind of first, question as to the apparent circularity. So we're taking kind of ontologies like FoodOn as the kind of as the atomic components here, and we're just kind of assuming that they're already built and they're high quality and they're great and so on. And then what we're trying to do is to build a recipe knowledge base in quotes ontology that are compositional classes that describe how these things connect together in individual recipes. So that's maybe resolves the kind of apparent dichotomy there. And then in terms of the magic, so the way the tool will work is it will, when it generates the prompt, it will ask the model, give me back all of the steps semicolon separated. And you just, the very weird thing about these language models is you can just ask for things and they will and they will give you them back. They don't always obey you. Sometimes you ask for a semicolon separator and it will give you something as a markdown list. So there's a few hacks that you've got to kind of do and kind of prompt tweaking and so on. It's a bit of an art, but yeah, that's essentially the way that it works.
And just to be sure, for your language model, you have trained the model with some phrases?
We didn't do any training. We are using, this works with, we have only tested it with the really large, GPT-3.5, GPT-4 available from OpenAI. In theory, it can work with any instruction tuned model. In practice, I think a lot of the open source instruction tuned models are just not quite there yet, but I'm hoping that they will be in the future.
Thank you.
I'll squeeze in just, so one little thing, I tried ChatGPT looking up sesame seeds and so on, and it reported back, give me a URL for sesame seeds in an ontology, and it gave me back FoodOn, but it made up the IDs for the terms. And in fact, it made up even the URL. It was referring to the FoodOn website ID whatever, which it exposes what it's good at and what it's not good at, which is this predictive character and word.
Absolutely, yeah. And hallucination is a big problem, but if you constrain your task in a certain way, like if you just ask it from its own knowledge base, give me the FoodOn IDs for this, it will hallucinate. But you can do things like give it a piece of text and say, give it a very constrained task, and we tend to find that it hallucinates a lot less for doing this kind of thing.
I'm going to squeeze in one other question, which follows Magali's. You had to gloss over LinkML because you didn't have much time, but is this truly a two-part exercise here? One, ask ChatGPT or OpenAI whatever questions to fill in the LinkML model from free text.
Yes.
That's step one. And then step two is try to do a good job of matching to ontology both the terms, entities, and then secondly, axiomatizing it.
Yes. In fact, it's multi-part, yes.
Okay, Kyle.
Yeah, on your slide, I wanted clarification. You mentioned sort of parsing out melted and sauteed and putting that in your list, but lost that, at least on the slide, that it was the butter that was melted and it was the onions that were sauteed. Right. Is that something that is just a limitation of the system or something where you can retain that level of information? I ask because on our end, retaining that sort of linkage could be really important. To understand what's melted versus what's sauteed.
To us, I don't have a great answer yet in this particular kind of case. There's at some level, there's a kind of a limit to what is available kind of in the text. And, sometimes there's maybe some domain knowledge, and being able to kind of tease those things out, but it's probably not doing a fantastic job at doing things at that level of granularity yet, but I think that would be a great thing to work on next.
Great, thanks.
And Catherine, I presume that this is, you guys have been pondering possibly how it is that one could take a content in another language on Wikidata and use that as the material to ask a questions of with respect to translation and so on. But have you heard of anybody heard anything around the translation opportunities here? That's pitched to anybody, including you, Chris.
Yeah, we've tried a few kind of experiments that way. I mean, I'm quite interested in how we can make use of kind of translation of kind of like the more atomic parts of FoodOn, like Apple, to some of the more compositional classes as well. So there's a few different approaches we could take there.
But clincher is we'd have to train OpenAPI on Wikidata or Wikipedia articles in a language in order to get anywhere.
You could try fine-tuning, but I always say before you try fine-tuning, just try in context learning. Just give it examples and see how well it does there.
Okay. Anything else from the floor? We're over time a little tiny bit, so I guess then we can give it a wrap. And thank you both for presentations that could have easily been dedicated to an hour or two each. But I really appreciate all of this and look forward to seeing you guys again in a month. So thanks, Chris.
All right. Thanks, everyone. Bye-bye.
Bye.